polite and customary and humanly absolutely appropriate to thank the organizers of a conference or program. So for the record, let's consider that I have spoken for 4 minutes and 30 seconds, plus the real 30 seconds that makes 5 minutes. I hope to have as much time by the end of the talk to really say what I think of this program and other programs. Actually, it was 5 years ago in the framework of a program run by this institute called Interaction and Growth in Complex Systems that Yuri Sukhov suggested to take a look at interacting particle systems in a random environment. And his suggestion, to be more specific, was to take simple systems with a few particles, but not with 2 to begin with. My reaction was, Yuri, people will laugh. He said, let them laugh, let us work. Okay, so now in the second part of the talk, which will more or less at the level of graduate seminar, I will present results and elements of proof, which we also presented on September 30 in the framework of this program on a seminar, on the institute seminar, concerning spectral localization for any number of particles on the lattice and in the continuum. As far as the lattice version is concerned, there are 2 papers, both accepted, one in communications, the second in mathematical physics, analysis, and geometry, and both works are available in archive. For the continuous version, this is a work in preparation, and I hope that in our larger team it will be made public quite soon. So here's the plan. The first 3 sections is the first part of the talk, and I will try to make the first part of the talk as simple as possible. Kolmogorov once explained what is a good structure of a good talk. The first part has to be available to everybody, the second to experts, and the third one, well, bad tongues say that often his own talks were reduced to the third part. I will try to stick to the first 2. So after a very good lecture, I would say, given yesterday by Simona Varzel on their joint work with Michael Eisenman, I will try to organize the first part of the talk as a series of simple exercises. But in the university where I teach, students never remember tomorrow what was taught in the lecture course yesterday. So let me start with some reminders. We start with a single particle model. Classical, conventional, well known for more than 20 years, single particle model. I mean, known as mathematically treatable, doable. Here we take a second order Laplacian plus a potential, which is a random field on the lattice ZD, and to remain in the simplest possible case, just consider the case of a random field with a marginal density, which is not necessarily a useful condition, but well, it's a simple and widely used. A more general condition is here, but let's not pay too much attention to more difficult case. Now, to prepare the end of the first part of the talk, let us introduce also the n particle Hamiltonian, which may be considered on the lattice or in continuum. And to avoid many questions about particular form of the interaction, let's stick with the simplest case of a binary or 2-body interaction although, as Simona explained yesterday, many other kinds of interaction can be of at least of short range. Short range may be treated in the same way as binary interactions. Now, we will use this geometrical notion of a box, which is actually a ball in a soup norm. For technical reasons, it is convenient to take this ball of radius L minus 1, so that its exterior boundary will be a distance L from the center. And boundary without superscript minus or plus is the pair of hopping sides connected by the Laplacian. Now, to briefly remind the historical context, it is not a review of all results, just some points most relevant to this talk. For physicists, localization is much wider and deeper object, and there are, as physicists say often, several signatures of Anderson localization. So yesterday we heard a talk about the dynamical localization. The spectral localization will be the subject of the second part, and now in the first part we will stay with the phenomenon of exponential decay of Green's functions. So you see, one can say that in the framework of this program, 50 years after, the first mathematical result came, roughly speaking, 20 years after, in one dimension. Multidimensional results came, roughly speaking, 30 years after. So it took some time. Now, in '86, Simon and Wolf, which reconsidered an idea used earlier by Cantani, gave a simple, soft way from the signature number 1 to the signature number 2. And anticipating your questions, I have to admit that so far I am unaware of any soft way of that kind for multi-particle systems. So the results of the first part of the talk will concern exclusively the first signature. Now, among the papers which are cited when we speak and we deal with localization, there is a paper which is cited less often than others, maybe because of its size. But actually, this paper, as you see, takes 10 pages. 5 of them are dedicated to quasi-periodic systems, and only 5 to random Schrödinger operators. In these 5 pages, there is a tiny piece, if my memory is correct. It's 5 lines of text plus 2 equations, which is the hardcore, the heart of the proof of the first signature of Anderson localization for random Hamiltonians for one particle in any dimension on the lattice. And that is remarkable. Now, during this program, I had many contacts with physicists, and it, well, I have to admit that I learned too many things, and probably more from physicists than from my colleagues mathematicians. And it was actually due to my collaboration with Boris Shapiro, initiated by Tom Spencer. Many thanks. That I have been taught by Boris the shortest and the most efficient course of multiscale analysis, which resulted in a very simple proof of not only single but multi-particle localization at the level of Green's functions, which I'm going to present you. Now, so far we are in exercises on single-particle Hamiltonians, and let's remind some elementary facts like resolved identity and its application to Anderson Hamiltonians, which goes through the observation that the Laplacian is, after all, a sum of hopping operators, So taking a contour in a given box, we can decouple Laplacian and therefore Laplacian plus multiplication operator, the potential, into sum of two operators living either inside or outside the contour, plus, of course, as a perturbation, the Hopin terms across the contour. This way, we come to the geometric resolved identity, that's what it is called, and taking in account that gamma equal the elements of matrix element of gamma are equal 0 to 1, and taking by absolute value, we come to the geometric resolvent inequality. Now, to go further, we have to introduce a few notions and a warning for physicists. When you see something resonant, most likely it is not resonant at all in the way you see resonance. When you see something singular on the screen, most probably it is not singular in the way you see it. It's just technical terms, sort of slang. So we will call a subset non-resonant if the resolvent is not extremely, but polynomially or sub-exponentially large, meaning that the energy at which we take the resolvent is not extremely close to poles of the resolvent, that is, to eigenvalues. Well, how to estimate the size of the resolvent, say, the norm of the resolvent? It seems to be a complicated matter, which it was before the celebrated paper by Wegener, which gives us this estimate. It's a particular application of Wegener lemma, of course. And there are many extensions now with assumption or without assumption of existence of marginal density. Log-Hölder continuity or log-Hölder continuity of marginal distribution is more than enough. Now, a notion which looks more innocent is a notion of singular or non-singular box. We call it non-singular if the green functions feature exponential decay phenomena behavior in this box. If the decay is insufficient for our technical purposes, then we just call such a box singular at the energy E. Now, a few observations about singular and non-singular boxes. If a smaller box of size L-1, I recall you that the radius of this ball is L-1. Inside the larger set, for example, again a cube, is non-singular, then by the geometric resolved inequality we just saw on the previous slide, we have the following abstract version of the geometric resolved inequality for a function f defined as a g of x, y, e, with e fixed and y as the boundary fixed. This way, we just get rid out of annoying notations. And if you have been typing, like Yuri and I were typing for a couple of years, 5-level subscript and subscript equations, then you will appreciate getting rid of these Green's functions in the inequality. Now, so this reminds a sort of subharmonicity, which will appear on the next slide. But what happens if a box is singular? That is, there is not enough decay of Green's functions inside. It may be very singular. We may be at the pole, and there we can do nothing. Or it can be gently singular. If it is gently singular, then, as we will see on this picture, we can do the following. If there is a problem with any point inside a box, which I put, well, it was supposed to be pink. Now it's a rather brick, stone brick color. So if inside this box there is a problem, then we apply a geometric resolved inequality in 2 steps. First, we step out as far as to find boxes which are painted here in white, in which resolvents decay exponentially, which are non-singular. So this step gives us a factor, which we saw on this, which we see on this slide, which is sub-exponential. But now, making the second step from the center of the neighboring box to its boundary, we get exponential decay. Well, gamma was already introduced. I just remind that making it gamma of ml, that is multiplying m, multiply m by 1 plus something, allows to avoid rescaling of mass, so to say mass, from one scale to another. The real arithmetics is running on the background, but not even in notations. Now, so we see that if we have a gently singular box, then we still have, for the function f defined in the same way, a similar bound. Well, actually, this q tilde and this q are slightly different, but take the maximum of them. They're both exponentially small. What is different between this and that blue equations is the reference set. The value of the function f at the center is q times less than maximum of a reference set. And this is a thin reference set, it's a thicker reference set. So here comes a natural definition. We make an abstraction of these observations, and given some set, but maybe even infinite, and a subset S, which we will call in a moment singular, we consider a function of this large set. It's called LQ, with small case L subharmonic, and non-singular outside the set S if this estimate holds outside the set S. On the set S, we require a slightly different upper bound with a different reference set, but the same decay factor. Formally speaking, q is not required to be less than 1, but of course, if q is bigger than 1, it's useless for the purpose of honest localization. So here, how it looks like. There are good squares, which are all in white, and there are gently bad, for which we do two-step argument. Now here comes a lemma, which says that if in a large box there is a singular set, by the way, anticipating equations, if S is empty, the whole argument is much simpler. But even if we have one singular set for this subharmonic function, and there is some space, some integer number r times small case L between the outer boundary and the set, and there is some space between the center of the larger box and the annual area, which covers completely this single set, then the decay of this subharmonic function from the boundary to the center, or if you like, from the center to the boundary, is roughly speaking as if it were in the case where there were no singular subset. Well, we lose the diameter in the exponent, the diameter of the singular set. Well, the proof is pretty straightforward. We start with we start with all points which can fit with entire small case L box inside the larger box. And if this box is non-singular, we have a decay factor of q going from the boundary to the center. So we can get a upper bound for the neighboring points by global maximum. So for any point inside this slightly smaller box, or ball, if you like, we have a global estimate, global maximum times just one q. We can continue, but stepping small case L towards the center, and on and on and on. Well, that goes smoothly until we stumble on a singular annular area. But remember, there's nothing really singular inside this area. So everywhere inside this area, in the white area and in the annual layer, we have a global estimate by global maximum m times the number of steps toward this area. Now we can continue making big step inside. Indeed, we have a global bound in the whole area, so we can continue from inside. And that proves the required upper bound for the function f. An immediate application, we just remember that our function f from the previous slides was a Green's function. So if we have a Green function resolved in a box which contains no singular subbox, then we have a good decay from the boundary to the center or from the center to the boundary. Well, if there is, by malchance, a singular area, then we have similar estimate. Remember that in this gamma, we improved m by small quantity, which allows to uniformize the bounds in both non-single and gently single case. Now, this is basically the heart of the proof of signature number 1 of Anderson localization in the 86 paper by Tom Spencer. Assume that we have two facts established: Wagner estimate and inductive estimate of on the probability of insufficient decay in the box, in a smaller box of size small case L. Then we can deduce from these two facts that the same estimate, the same kind of estimate, holds for larger scale L. And here, how it goes. We consider two events. First, R is the event that larger box is not completely non-resonant. I recall that in the definition of a complete non-resonance, it was required that the box lambda large L is itself non-resonant, and it does not contain smaller boxes which could be resonant from size small l and up. So this event is of small probability by Wagner. This event may only happen by the previous geometric lemma if you have at least one gently or strongly singular boxes of size small case L inside the larger box. But because we are in one particle case, in the presence of IED potential, if there are two disjoint boxes, they are independent, and so we arrive at the required upper bound for the probability of set S. Summing up probability of R by Wagner, and this one, we arrive to the required upper bound for the hypothesis S large case L. Basically, that's the proof of decay, exponential decay of Green's functions for single particle lattice case in presence of IED potential, which is entirely due to Tom Spencer. As I told, it's a 20-year young result. Now, let's come to the multi-particle case. What is striking is that making the step from one particle case to multi-particle case, at least on the lattice, and as Peter Stallman recently explained us in our discussion, it can be reformulated almost verbatim in the continuous case. This step at the level of Green's functions. This step takes, roughly speaking, 1 page of text. And the heart of the proof is basically half-page proof. So now we replace the inductive hypothesis S by MS for multi-particle singularity. This time we require more in this hypothesis. We require that for all numbers of particles less than n. And for all scales, for particle systems with smaller number of particles, this bound be established. So this is inductive in n, and for any given small n less than a large n, it should be proved by multi-scale. Now, to prove that for any scale we have multi-particle decay estimate of Green's functions, we have to prove ms L sub k plus 1, knowing ms L sub k for a given energy interval n and the same number of particles. Reading carefully the proofs of localization by Fröhlich, Spencer, Martinelli, Coppola, and von Dreyfus-Klein, we can see that actually the exponent p measuring the decay of probability of singular sets can be made arbitrarily large at the cost of either taking large disorder, or going deep in the low energies, or rather to say extreme energies. Now, I have to speak a little bit about the decomposable systems, that is, n-particle systems which are clustered in at least two groups which are sufficiently remote so as to prohibit any interaction between them. Now, if we take the indices labeling the particles and decompose them, partition them in two sets, J and its complement, we can always renumber the particles so that the first group would contain the particle number 1, 2, 3 up to n prime, and the complement the others. And we suppose they are remote, so that the short range interaction vanishes, completely vanishes. We also suppose that n-particle box of size L is non-resonant, and actually, yes, non-resonant. And we suppose also that both projections on the first particle group and the second particle group feature exponential decay of Green's functions in their respective projected boxes. Under these conditions, one can prove that the n-particle box of size L is non-singular. That is, for a decomposable n-particle system, a sufficient condition of localization at the level of Green's functions is that it is non-resonant, and it has good projections on smaller particle groups. Well, here is the proof. I don't have to explain the details of the proof because yesterday we heard it in a different version by Simona, who made a Cauchy integral. Well, personal remark why there is no Cauchy integration here, because I'm working in the university where for most math students Cauchy integral, depending on the year, is maybe a hard topic. So I prefer to stick here with finite sums. Okay, so the proof is exercise. Now, let's formalize this notion, which proved to be useful, right? Decomposability. As a remark, a geometrical remark comes here, saying that n-particle boxes far enough from the diagonal x1 equals x2, that is very far from extremely compact, extremely clusterized systems. Such boxes have to be decomposable. Now, the following lemma, it's the last preparation lemma before the proof of multi-particle decay of Green's functions, says that the event that n-particle box of size Lk, of radius Lk, is singular. This event is covered by the following two events, well, the probability of which appear in the right-hand side of this inequality. The first is that the box can be resonant. This is ruled out, or rather say controlled by vector estimate, vector or vector type estimate. The other event is that at least one projection, the box is decomposable, but at least one projection has to be to feature insufficient decay of Green's functions. If that is the case, we apply the previous lemma and we are done. Now, this is the formulation of the inductive step, which leads directly to the conclusion, once proven, that multi-particle decay, the exponential decay of Green's functions for multi-particle systems on the lattice holds at any scale. Here's the actual proof.
What's the actual statement that's proving it?
Huh?
What's
It says that if
what's the main theorem that you're proving?
here, this is the main theorem.
Okay, but if I go back to the n particle system.
Yeah, it
Earlier, but
okay.
What was the main theorem there?
It wasn't formulated there. Okay, so basically this lemma, I call it lemma because, well, actually a simple statement, says that the exponential upper bounds with high probability, high enough for any reasonable purposes, in boxes of size Lk, for energies inside a given interval I, for any fixed number of particles Ln, hold whatever be the number of the scale. Holds in any scales. We start with L0.
So it's enough to check if it's on large box.
Yes. It was shortly said at one slide. Let me repeat it again. That verification of this hypothesis for k equals 0 is not really sensitive to the presence of interaction. The proof goes in the same way, literally in the same way, with or without interaction. Of course, the probability, the phenomena is not the same, but the upper bounds, rough upper bounds, rough still sufficient, are the same with or without interaction. So here's the actual proof, and as you see, there are again two events which cover the event that the larger box of size L sub k plus 1 is not is singular. The first event is lack of complete non-resonance of the larger box, meaning that either the box itself is resonant or it contains smaller boxes of size Lk and up inside it. This is ruled out by Wegner lemma. Now, assume that there is a singular box, that is not necessarily close to the spectrum, energy not close to the spectrum, but there is not enough decay of Green's function inside it. If it is decomposable, large distance from the diagonal means it's decomposable. If it is decomposable, we apply one of the previous lemma and say for the singularity, we have a small probability, small upper bound for the probability. Now, assume that we have two boxes which are singular and which are not close to the diagonal, that is, both are non-decomposable. Let me check where a good, yeah, okay. So here is the good picture. There are two boxes, both touch or nearly touch the diagonal. They are remote, therefore their projections are completely disjoint. And so are the potential samples in these two boxes. Then we can run the same argument as in one particle case which I showed you, which proves that the probability of this event is bounded by, well, square, which is less than we require. Summing up the probability of S and B, we get the required upper bound for the probability. And if neither S nor B occurs, the larger box cannot be singular by the previous lemma. Well, one of the previous lemma formulated in abstract form for LQ subharmonic functions. Now, this marks the end of the first part of the talk. So I hope I convinced you that all proofs are short. It takes some time to read them. This is available in a preprint recently uploaded to archive. And I have to say that 90% of this proof is due to old paper by Tom Spencer. The 10 remaining percent are shared between Bourgain, Goldstein, and Schlag, who used the elegant geometric lemma which I showed you with this radial descent, rather radial expansion. And Boris Shapiro, who explained all that. For a long time, for about 2 months, Boris refused to co-sign a paper saying that it's not a human language that I'm using. But yesterday, he said, OK, if you agree to rewrite it in a human language, I will co-sign it. OK, now the exercises are over, and let's start a short graded seminar where I will present and only outline the proofs for spectral localization. Now, this time it will be spectral localization on the lattice, and as we will see, also in continuum.
So what you showed us before is what? The decay of the Green's function.
Right.
Is that correct?
Right.
Now you're going to tell us what about the
Eigenfunctions.
Okay.
Spectral localization. Spectral localization. So in my list, it was second signature. And as we know, there is only one proof by now for the third signature, that by Eisenman and Warzel. For now. OK, so on the lattice, we assume we have ID field. A random field. It is the simplest case, although non-deterministic case, non-deterministic random fields can also be included. But let's stick with ID fields. Well, this time, let's say honestly, we don't need the existence of marginal density for the potential. Any holder exponent does the job, and log holder with sufficiently large constant also does the job. It is, I think it is not written on the slides, but there were questions yesterday about the hardcores. We can assume hardcores both in the lattice and in the continuum because it doesn't interfere with our proof. Just a restriction to a sub area. That's it. Now, the hardcore can be combined with a bounded potential outside the hardcore. So in the traditional cases of large disorder of extreme energies, often referred to as low energies, for extreme energies, energies we can prove the exponential decay is probability 1 of eigenfunctions in a given interval, or if we are, for example, in presence of a bounded potential everywhere for all energies. Now, this is one possible result in this direction. It would take more time to speak of all possible formulations. Assuming that the potential is ID and say holder continuous, there for any given mass m plus, which would like to appear as the Lyapunov exponent, so to say, or the exponent of decay of eigenfunction, we can find as a threshold, large threshold for the amplitude of the potential, which guarantees such a decay of eigenfunctions in a given energy interval I. Okay, in continuous case, which we treat in a larger team now, we can treat several types of the external potential. One is already in an archive. even actually two are now in archive, the first and the second. Alloy potential with scatters on a d-periodic sublattice in RD. Also improving, well, technically improving an earlier result by Fischer, Hupfert, Leschke, and Müller on Gaussian fields in a single particle case. We prove necessarily estimate, basically vector type estimate, a weak form of Wagner estimate, also for random fields generating potential with continuous argument. Well, alloy with, say, Poisson supported scatters just takes more time because formulation, general formulation of all conditions which would be sufficient takes a couple of pages to cover all. So we just postponed it to a forthcoming paper. But the first two results at the level of Wagner estimates are now in an archive, and the localization is in preparation. So under these conditions, one can prove a result similar to that. Specifically, this is one possible result in this direction. In the continuum case, take a periodic alloy with independent amplitudes omega of the scatters with bound functions v. We suppose that the support of each bound function is finite. We also suppose, and this is a simplification, it is not necessary, now it's well understood, it's not a necessary condition. By analytic continuation, by unique continuation, we can do more, one can do more. But we assume the simplest case that the bound functions cover all the space. Okay. And under these conditions, again, for amplitudes which are, for example, Hölder continuous, have a Hölder continuous distribution, one proves the exponential decay of eigenfunctions in an energy interval close enough to the ground state energy. Well, now the outline, for which I don't have much time. So I probably just will show you a few illustrations, a few pictures which show the essence, the geometrical nature of our proofs. Again, to use multi-scale idea, we have to prove a lemma of that kind. Two boxes, so to say, in a general position are simultaneously, for the same energy, singular with a small probability. So why is it so? Well, there are three possible cases for this pair of boxes. They are both decomposable. Decomposable means that each of them is decomposed into two subsystems, and the projections, the configuration projections of these subsystems are disjoint. And both projections, which Peter Sturman proposed to call a shadow, the shadow of the first box is disjoint with the shadow of the second one. Then we don't have to use induction. We just use the lemma about the decomposable boxes of the same kind as I showed you in the first part of the talk. The second part seems to be the hardest one. But if we think a few minutes, you will understand this is probably the simplest case, because this is the case done 20 years ago. Why? Because now the shadow of these boxes are disjoint. Decomposable or not, they are independent. If they are independent, that all it takes for, say, von Dreyfus and Klein proof is to count a number of such pairs which are independent, and the proof goes exactly along the lines of the von Dreyfus Klein proof, verbatim. Now, the third case is bureaucratically the most complicated and cumbersome. I have no explanation. I confess I have no explanation of why so far we were not able to find a simple proof for the third case, but that's the fact. So actually to prove that such a pair where one box is non-decomposable. It's really clustered system. The other, non-clustered system, compact set of particles. And the other is clustered, decomposed, is simultaneously singular with small probability. Well, it takes a bit more to go inside these boxes, and so to say, to study the anatomy of these boxes. The decomposable box is either resonant or it has at least one singular projection. Both events can be estimated. The probability of both events can be estimated in the same way as in the first part of the talk. So assume it is resonant. If it has singular projections, then it has a small probability. If it is if it is non-resonant, and if it doesn't have any singular projection, it is non-singular. But our assumption it is singular, right? Because both are. Now this guy, suppose it is resonant by Wegener and our extension of Wegener lemma for a couple of volumes. The other should not. Otherwise, the probability would be small. Well, to be singular, being non-resonant, it has to contain, again, using a verb in a verbatim form, von Dreyfus-Klein method. We can say that the only way to singularity, being non-resonant, is having too many singular subboxes. But again, what can be those subboxes? Either decomposable, we apply the argument number 1, or non-decomposable, we apply the case number 2. So this way, there is a bounded number of non-decomposable boxes inside, say 8 or 10. There is at most one decomposable, and it is done. So here are the references. Let me go to the end as shown again and say that the signature number 1 by 90% was proved exactly 20 years ago. Okay, and unfortunately, this paper so far has no extension to multi-particle case. Otherwise, the first signature would imply in the n-particle case the second one. Thank you. And maybe now I can say a few words about what I really feel about these programs. From my personal perspective, these programs, I participated in 3 programs in 5 last years, were most enriching. And as far as our joint program with Yuri is concerned, the first step towards the localization under restrictive condition of analyticity of marginal distribution for 2-particle case was made in the frame of the first program in interaction and growth on complex systems. The second step toward a generalization for any marginal distribution was made in the frame of another program, analysis on graphs and applications. And in the frame of this program, we completed our n-particle proof, and also Boris Shapiro explained me how simple is the proof of signature number 1 in the n-particle cases. So let's say again, this institute is fantastic, and all its not staff team is. The programs, and especially this program, where there have been many physicists sharing with us, and particularly with me, their physical insights, are extremely well organized. So I thank the institute. I thank the organizers, because when we worked, they couldn't. I know it for sure. We worked very well because they didn't have enough time to work it themselves. But there is one a modest entity on the second floor which is really thanked. So let me thank this in a welcome way and say, live long and prosper, the tea and coffee making machine on the second floor. Thank you.
Let's see if there are some questions about the talk. I have some questions of my own, but let me see whether there are other questions. Yes.
I'm a bit surprised that you never have to consider 3 cubes at the same time. I mean, because if you have 3 cubes in an IP position, you have no independence left whatsoever.
In this case, I pictured 2 cubes to say that the probability of such pair of cubes to be singular at the same energy is small. But if we have more, we have to consider in this case more pairs. But if all pairs are disjoint, the probability for them to be disjoint is a product. And I said this part of argument goes exactly as it goes in a single particle case, where it is known that we have to consider several pairs. Thank you for the question.
Any other question? I have a quick question because I know you and Boris talked quite a bit.
Yeah.
And but I expected to see this other representation in which you diagonalize you take the interactive.
It is still, yeah, it is a better approach. Many physicists who asked me how does it work.
Maybe you should make this comment of mine clear to the audience because I don't think they understand.
Yeah, okay. So actually, the question is about the following: is this approach and or this kind of approaches, both ours and by Asman Warzel, which is an adaptation of single particle point of view to multi-particle system, is it correct? Is it appropriate? From many points of view, it is clear it is not, because we pretend that the system is a single particle. It's a simple adaptation. But the particle consists of, the system consists of many particles. We know that in absence of interaction, that would be localized by trivial reason, because eigenfunctions are tensor products. The physically appropriate question is, how can one use the fact that the interaction is a mere perturbation? The answer should go in a different way that used so far by Eisman, Warzel, and by our team. A good starting point has to be a non-interacting particle system, say under large disorder or lower in the energies, with good localization everywhere or in the energy interval. And then, at least perturbatively, one probably should treat, it's my opinion, one should treat the interaction as a perturbation. So, along in this perspective, I think more appropriate result can be obtained, and physically interesting result can be obtained. Otherwise, it is, well, Simona told it yesterday, if you try to go with n to infinity, any estimate, any constant explodes. Why? Because if you take n dimensional single particle system, it does explode.
So, I mean, what I understood is you just changed your basis. I mean,
right.
So you go to a basis of eigenstates.
Yes. So the right starting point is a basis of tensor products of one particle, single particle, localized eigenfunctions.
So is that work in progress too, or?
It's in progress.
Any other questions or comments?